In this video, we will be taking a look at section 1.3, which covers rates of change in behavior of graphs. So we're going to start by talking about the rate of change. And when I hear rate of change, I think of slope. So the rate of change is a description of how the output quantity changes in relation to the input quantity. The units on a rate of change are output quantities per input quantities, or input units, sorry. The average rate of change is the total change of the function values, which are our output values, divided by the change in the input values. So our average rate of change is given by our change of output over the change of input, which we might write as delta y over delta x. And that formula is y2 minus y1 over x2 minus x1. This should remind you of the slope formula because that's exactly what it is. Y2 minus y1 over x2 minus x1. That gives us our average rate of change. So we're going to take a look at this graph, and based on the graph, we want to find the average rate of change on the following intervals: -1 to 2, 0 to 2, and 1 to 2. So what this is saying is if I go from x equals -1 to x equals 2, what is the average rate of change between those points? Well, since these are x values, I need the associated y values. So let's see what those are first. If x is equal to -1, then on my graph, I'm right here, and the y value there is +1. If x equals 2, then I find x equals 2, which has the point here, which has a y value of 4. So we have 2, 4. Now that I have these points, I'm going to be able to find my average rate of change using the formula. y2 minus y1 over x2 minus x1. y2 is 4 minus y1 is 1. x2 is 2 minus x1 of -1. 4 minus 1 is 3. 2 minus a -1 is 3. And 3 divided by 3 is 1. So it's saying the average rate of change is 1. Let's go from 0 to 2. If x equals 0, then y equals 0. And we already know if x is 2, then y is 4. If we plug into the formula for average rate of change, we get 4 minus 0 over 2 minus 0, which is 4 over 2, which gives us 2. So the average rate of change between 0 and 2 is 2. Finally, we have 1, 2. If I use an x value of 1, then my y value is 1. And again, we know if x equals 2, then y equals 4. Plugging into the formula, I get 4 minus 1 over 2 minus 1, which is 3 over 1, which is 3. I'm going to show you what this means in terms of the graph. So if we go from an x value of -1 to an x value of 2, the average rate of change to get from one point to the other is 1. The slope of that line is 1. Does that mean that on the actual graph, I'm always increasing at a rate of 1 y value for each x value? No. In fact, I start by decreasing, and then I'm increasing, and then I'm increasing, and then I'm increasing. Over here, I'm getting more and more positive. But if I were to average out all of these different changes, they average out to this average rate of change of 1. If I were to go from an x value of 0 to an x value of 2, you see kind of the same thing. If I could draw a straight line, my average rate of change is 2. If I did the same thing from 1, I'd just be jumping from x equals 1 to x equals 2, and that would be a line with a slope of 3. So that's what it means graphically, but you've seen how it works algebraically as well. We're now going to compute the average rate of change using the algebraic form of the formula and see what we can do with this. So it says to compute the average rate of change of f of x equals 2x squared plus 4 over x on the following intervals. You will want a calculator for this part because we're going to get into some pretty gross fractions. First up, I need to know f of 1 and f of 3. So I'm going to start by plugging 1 in. I get 2 times 1 squared plus 4 divided by 1. That gives me 6. So f of 1 is 6. If I plug in 3, then I get 2 times 3 squared plus 4 divided by 3. Whoops, messed up something. 4 divided by 3. I get this decimal number. If I press my math button, enter, enter, that's going to take it to a fraction for me. And f of 3 is equal to 58 thirds. Now I can use the average rate of change formula, because f of 1 equals 6 means I have the point 1 comma 6. F of 3 equals 58 thirds means when x equals 3, y equals 58 thirds. So I have my 2 points. I just need to plug them in. So I'll have 58 thirds minus 6 over 3 minus 1. So let me go ahead and type that into the calculator. If you have a fraction button, now would be a great time to use it. If you don't, then you can type in 58 thirds as 58 divided by 3 in parentheses. So I have 58 divided by 3 in parentheses minus 6 equals, and I want to divide that by 3 minus 1. If I go math, enter, enter, I'm getting 20 thirds. So the average rate of change of this function on the interval 1 to 3 is 20 thirds. Let's try the next one. We're looking at the interval 1 to 5. I already know that f of 1 is equal to 6 because I plugged that one in already. Now I need f of 5. So I need to plug in 5 to the original formula. That's 2 times 5 squared plus 4 divided by 5. Math, enter, enter, tells me that f of 5 is equal to 254 over 5. To find the average rate of change, I do my y2, 254 over 5, minus my y1, 6, over my x2, 5, minus my x1, 1. So that's going to be 254 divided by 5 in parentheses, minus 6 equals, divided by, in parentheses, 5 minus 1, equals, math, enter, enter, 56 fifths. The last one we want to do on this slide is looking between 1 and 1 plus h. This looks really complicated and it's going to take some space, but as long as you follow the same steps we've been following, we'll be okay. I'm going to start on a blank whiteboard just so I know I have enough space. We're looking at f of x is equal to 2x squared plus 4 over x. We want to look on the interval from 1 to 1 plus h. I still need to find the y values associated with these. I already found f of 1. That was equal to 6. Now I need to find f of 1 plus h. You might be asking yourself, well, how do I find that? We find f of 1 plus h the same way we found f of 1. We plug in 1 plus h for x. So in this case, that's going to be 2 times, what am I plugging in for x? 1 plus h. Well, that x was squared, so my 1 plus h also needs to be squared. But I'm not done yet. I still have the plus 4 over x. So I have plus 4 over what I'm plugging in for x, which is the 1 plus h. Well, 2 times 1 plus h squared does not look like fun at all. And the plus 4 over 1 plus h, that really doesn't look very fun either. But let's see if we can simplify it. I'm going to start with the 1 plus h in parentheses squared. We have to remember that if something is in parentheses squared, that means that it's multiplied by itself. So this is going to be 2 times 1 plus h times 1 plus h, and we still have our plus 4 over 1 plus h at the end. I'm now going to FOIL out those 1 plus h's. So this is 2 times 1 plus, on the outside I get an h, on the inside I get an h. So that's a total of 2 h's, plus h squared, and I still have my plus 4 over 1 plus h out back. Now I can distribute my 2 through the parentheses. So I have 2 plus 4h plus 2h squared plus my 4 over 1 plus h. It's not pretty, but I have it. So now the points I'm working with, my x value is 1, my y value is 6. My x value was 1 plus h, my y value was 2 plus 4h plus 2h squared plus 4 over 1 plus h. Now I can plug into my formula, the y2 minus y1 over x2 minus x1. My y2 is that nasty gross one, 2 plus 4h plus 2h squared plus 4 over 1 plus h, minus my y1, which was 6, over my x2, which was 1 plus h, minus my x1, which was just 1. Let's see what we can do with that guy. So in my numerator, I have a 2 minus 6, which gives me negative 4. I still have a plus 4h plus 2h squared plus 4 over 1 plus h. That's all over 1 plus h minus 1, just leaves me with h. Now that's really gross if you ask me. So what I'm going to do is I'm going to break this up into a bunch of different fractions and see if I can simplify it. So because all of these are over h, I can break them up into separate fractions, all with the denominator of h. So I have negative 4 over h plus 4h over h plus 2h squared over h plus 4 over 1 plus h over h. Well, what does this guy mean? 4 over 1 plus h over h? Well, mathematically, that means 4 over 1 plus h divided by h. If we want to divide fractions, we can keep, change, flip. So I keep the first fraction, 4 over 1 plus h, change from division to multiplication, flip, it was h, which I can think of as h over 1. So when I flip it, it's 1 over h. 4 over 1 plus h times 1 over h gives us 4 over h times 1 plus h. So let's make that substitution. We're looking at negative 4 over h plus 4h over h plus 2h squared over h plus 4 over h times 1 plus h. Now I have a little bit of a hunch. I see that my first three fractions have the same denominator, but this fourth one doesn't. I want to see if I can make everything have the same denominator so I can crush them all together back into the same formula. My least common denominator is h times 1 plus h. All of these already have the h, so I need to multiply my numerator and denominator by 1 plus h. If I do that, then I'm looking at -4 times 1 plus h plus 4h times 1 plus h plus 2h squared times 1 plus h plus 4 all over that common denominator of h times 1 plus h. You're wondering, why would we do this? Just you wait. I'm going to distribute through the parentheses. -4 times 1 plus h is -4 minus 4h. Distributing the 4h, I get plus 4h plus 4h squared. Distributing the 2h squared through, I get plus 2h squared plus 2h cubed plus the 4 out back, all over h times h plus 1. But wait, I have a -4 and a plus 4, a minus 4h and a plus 4h. I also have 4h squared plus 2h squared, so those can combine to 6h squared plus my 2h cubed over h times h plus 1. I can factor my numerator. There's a greatest common factor of 2h squared that I can pull out, which leaves me with 3 plus h over my h times h plus 1. One of my factors of h cancels out, and I'm left with 2h times 3 plus h over h plus 1. Believe it or not, all the way back here, we had this really gross, disgusting expression, but we were able to take it all the way down here to something really not that bad. If you wanted to, since nothing else factors out, we could distribute the 2h through the parentheses, and we'd be looking at 6h plus 2h squared over h plus 1. That doesn't look too bad. Not to me, at least. So when we are dealing with h plus 1, these more variable included problems, there's going to be a simplification process, and it's going to take time. But honestly, having these problems in here are preparing you for calculus, because you're going to be doing these things all the time in calculus. All right, let's get this one out of our hair. Kind of bring stuff back on a little bit simpler level. Definitions. First up, we have increasing. Function is increasing on an interval if the function values increase as the inputs increase. We read graphs left to right like we read books. So increasing means going up. It could be increasing like this, it could be increasing like that, it could be increasing like that. As long as we are going upward, we are increasing. Similarly, decreasing means going down from left to right. So a function is decreasing on an interval if the function values decrease as the inputs increase. So we're going down. A local maximum is a point where the function changes from increasing to decreasing. So if we were going up and now we're going down, that top point is going to be a local maximum. It's going to be on the top of a hill. A local minimum is a point where a function changes from decreasing to increasing. So if we're going down and then we start going up, that bottom point is going to be a local minimum. It's the lowest value in that little area. So we're going to take a look at this graph and see if we can figure out where it's increasing and decreasing and find any local extrema. When you see this word extrema, it just means maximums and minimums, or maxima and minima. So identify the intervals where the function is increasing and decreasing. Also locate any local extrema. So we want to know where it's increasing, where it's decreasing. We want to find any local max if they exist, and any local mins if they exist. So let's start with increasing. Increasing means we're going upward. So it looks like we start increasing here, and we're going up, 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 and then we stop going up. So we are increasing from x equals -3 until x equals -1/2. But we're also increasing again, starting about here, and if we pretend there are arrows on the end of this, then we are increasing from about 1.25 to infinity. We will union those two together because if we are in a place where we are increasing, we are either here or here. Something that tends to confuse students when we're writing these intervals for increasing and decreasing, we're always going to use parentheses, and that can kind of hurt the brain a little bit. The reason we do this, and I'm going to use -3 as an example here. If I am standing at the point where x equals -3, I am not increasing, but I'm not decreasing either. If I'm not increasing at that point, then I can't include it. So that's why I'm not. Let's look for decreasing. So again, if there's an arrow at the end here, we're decreasing all the way until we reach x equals -3. So from -infinity until -3, we're decreasing. And then again, from a -1/2 to a positive 1.25. Let's see if there are any local maxes here. So are there any places where we're at the top of a hill? Well, yeah, right here. The coordinates for that point are -1/2, comma, I don't know, maybe 0.25. So for the local max and local min, we want to make sure that we're using full coordinates, an x value and a y value. Let's see if we can find any local minima. So are we at the bottom of a valley anywhere? Yeah, right here and right here. So there's two of them. When x equals -3, y equals -3. And then again, we have another one at 1.25 with a y value of maybe -1.1. I don't know, as long as you guess relatively close, I'm going to be happy. So we have increasing and decreasing. Now we're going to take this one step further and look at concavity. So we're looking at concave up and concave down. A function is concave up if the rate of change, or the slope, is increasing. So we go from having a negative slope to having a positive slope. So this is concave up. A function is concave down if the rate of change is decreasing. So we were going positive and then we level out, and now we're going negative. So this one's concave down. And then we're concave up again because we go from having a negative slope to having a positive slope. But notice this kind of has an upward cup shape. This one has a downward cup shape. So concave up is going to look like an upward cup. Concave down is going to look like a downward cup. An inflection point is a point where the function changes from concave up to concave down, or vice versa. So where you switch from up to down or down to up, that's going to be an inflection point. So there would be an inflection point here and an inflection point here. Something to be careful of, there's 4 ways we can intermix increasing and decreasing with concave up and concave down. So we said concave up looks like an upward shaped cup. We have concave up decreasing. We're still on that upward opening cup. We just happen to be decreasing. Concave up increasing, we're on the other side of that upward opening cup. So we are increasing while being concave up. We have concave down decreasing, where we have the downward shaped cup and we are going more and more negative. And then we have a concave down side of the cup where we're increasing because we are getting less negative. We are going up, but we're still in that downward shaped cup. So we're going to take a look at this graph again, and we want to see if we can identify the intervals where the function is concave up and concave down, and we want to see if we can find any inflection points. So we want to look for concave up, concave down, and any inflection points. Concave up, we're thinking of an upward cup. So I see kind of an upward cup here, but I do see a downward cup here. So somewhere in this kind of general area, I'm switching from being cup up to being cup down. And if I had to guess, I'd say probably here-ish. Because if I cover it up, that all looks kind of up-ish. But once I start looking over here, it's more down-ish. Again, if you're in the general vicinity, I'm going to be happy. So I'm concave up from negative infinity until I get to this x value, which is -2. But I'm concave up again over here. I have that upward cup shape. Maybe here-ish. Kind of looks like where I might switch, maybe even a little bit further down. We'll use x equals 1/2 maybe, until infinity. I might have even been a little generous on this one. It's probably a little closer to 0 for my concave up. Maybe about here. So -1.8 maybe. I know you're not going to be perfect about these. Just kind of give me the general area of where we have an upward cup shape switched to a downward cup shape, and vice versa. So concave down is this downward cup in the middle, and that's going to be from my -1.8 to my positive 0.5. The inflection points are where we switch. So hey, I already drew in those points. I just have to come up with coordinates for them. The first one we said was at -0.8 for x. I'd say the y value there is maybe -1.3. And then there's another one over here at x is 1/2. I'd say that the y value is probably about -1/2. So you just have to be careful about increasing, decreasing versus concave up, concave down. Concave up, concave down is looking at the shape of the graph, whether it's opening upward or opening downward. Whereas increasing and decreasing is looking at where are you going up, where are you going down. So make sure you're paying attention to those. These ideas, increasing and decreasing and concavity, are also absolutely huge in calculus. So make sure you're grasping the ideas now and ask questions if you have them.